Hi everyone. So today we're going to be talking about section 11.2, which is about infinite series, which is an idea that arises naturally in the context of thinking about the real numbers. I'm going to apologize in advance for the fact that my kids are both home and they're being a little bit loud today, so you're going to probably hear them in the background. If you're willing to put up with the distraction, then I think we have some good things to talk about here, and I appreciate the affordance. So the first place we think about why we even want an infinite series is in the context of irrational numbers, or even rational numbers. So when we write down a number with places inside of it, like 3.156, say, what we're really doing when we write down a decimal expansion is we're writing a sequence of fractions that have been added together. And that's what a series is. It's a sequence that's been added. So this is 3 plus 1/10 plus 5 1/100ths plus 6 1,000ths. And the idea here is that any decimal expansion can be written in terms of these fractions. That's what the places mean, right? The tenths place, the hundredths place, the thousandths place, and so on. But irrational numbers, we learn, have infinite decimal expansions, infinite non-repeating decimal expansions. And so if you write down pi, this keeps going. It has an infinite series that represents it. So if pi is 3.14159 and so on, then when we write this, we can start the same way as the fraction that I've written above, 3 plus 1/10 plus 4 100ths plus 1,000th plus 5 10,000ths plus 9 100,000ths and so on. But that has to keep going. So there's an infinite number of fractions that we have to use in order to write down what pi exactly is. And so the idea here is, because this is an infinite list, in some sense, and we would need an infinitely long list in order to get the exact value of pi, I need to have some idea of what it means for that infinite list to converge to pi, that is, to add up to pi. And that's what we're going to be studying in this section, is going to be what it means to have an infinite list of things that are being added, what it means for them to add up to a number, and how we can get a handle on when that happens and when it doesn't. So a more classical, in the sense of the internet argument, is the idea that 1 is equal to 0.9999999 forever. That's a rational number. But if you wrote 0.9999 forever, what you mean is 9 tenths and 9 100ths and 9 10,000ths and 9 100,000ths and so on. So even rational numbers, we have to deal with the fact that it's possible that they might have an infinite expansion like this. Okay. So with that in mind, let's talk about what a series is. So a series is built from a sequence. So we start with a sequence, an, and then we add it. So when we write down an infinite list or an infinite sequence and we add it, the way formally that we write that is like this. We write a1 plus a2 plus a3 and so on. And because it's annoying to write out like huge sequences like this, we typically use a condensed notation, which is called sigma notation, which looks like this. And in case you've never seen this before, the reason we use sigma notation is because sigma is the Greek letter S. And so this means sum. Okay, so we're adding up this infinite sequence. So that's kind of a meaningless object by itself, because how do you add infinitely? There's not we have a sort of an intuitive notion of what that means. So what does this actually mean? All right, back in business. So what does this mean? So the basic idea is that if I start adding fractions together in a form maybe we're more familiar with, if you look at a sequence like 1/2, 1/4, 1/8, 1/16, and so on, if we take that sequence and turn it into a series, well, 1/2 plus 1/4 is 3/4, and 1/2 plus 1/4 plus 1/8 is 7/8. And if we keep going, it looks pretty obvious that, like, as I continue to add these things, that the sum of these, any finite sum, the more terms I add onto it, the finite sums look like they have a limit of 1. So we can formalize that notion by defining it to be what's called a partial sum. So start with a sequence, an. Okay, so that's a sequence, a list of numbers. And then if we add up just a finite number of those, that's a meaningful thing. I mean, a finite list of numbers can always be added. So we can define what's called the nth partial sum. And the nth partial sum is going to be the sum, say, from k equals 1 to n of ak. That is just the first n terms of the sequence added together. And we also give this a name, which is Sn. Okay. So really, when we're talking about an infinite series adding up, what we're thinking of is, does the related sequence of partial sums. So remember, there's this related sequence, right? So S1, S2, S3, S4, and so on, which has Sn in the list. This is called the sequence of partial sums. And what we're looking at is, does that sequence look like it's headed to some number? So if the sequence an looks like 1/2, 1/4, 1/8, 1/16, 1/32, and so on, that's the sequence generated by 1 over 2 to the n, and I add those, what does the sequence of partial sums look like? Well, 1/2 is just a half. A half plus a fourth is 3/4. 3/4 plus an eighth is 7/8. 7/8 plus a 16th is 15/16. 15/16 and a 32nd is 31 32nds. And this list is going to 0. I mean, that's going to turn out to be necessary, that the sequence has to tend to 0 if we're going to have any hope that the partial sums are going to add up to something. The partial sums are keeping track of, as I add more and more terms from the sequence onto the pile, does it look like it's headed anywhere? And these numbers look like they're headed to the number 1. So this particular series, that is the series that goes 1/2 plus 3/4, that 1/2 plus a fourth plus an eighth plus a 16th, that's what we're going to mean by a convergent series. A convergent infinite series is a series for which the sequence of partial sums has a limit. So because 1/2 plus a fourth plus an eighth and so on, which I should say is actually equal to the sum from k equals 1 to infinity of 1/2 to the k, has Sn tending to 1, that is the sequence of partial sums associated with that series is tending to 1, we say that the sum from k equals 1 to infinity of 1/2 to the k is convergent, and it is equal to 1. So we're sort of sweeping a bunch of stuff under the rug if we say something like, so if we actually say that the sum from k equals 1 to infinity of 1/2 to the k is equal to 1, we're really covering up a bunch of machinery in the same way we did with integrals that involved infinity, right? An infinite series is really secretly a limit. That this is the limit as n goes to infinity of Sn is equal to 1. So that's what this means. An infinite series converges when its sequence of partial sums has a limit. So let's reiterate that. An infinite series converges if its related sequence of partial sums converges. We won't say converges, has a limit. Which is the same as saying convergent, but I'm trying to separate that what we're studying in this section is the convergence of infinite series. But basically, an infinite series is equivalent to a related construction of sequences. That's why we studied sequences first. Okay. If an infinite series does not converge, it diverges. Doesn't converge, it is said to diverge. And the big question of this chapter is when series converge and when they diverge. And we're going to build a bunch of tools for figuring out when that happens. So let's actually look at an example here. Let's consider the sequence. Let's suppose, so here's an easy example. Suppose for some sequence, an, we have that Sn, the nth partial sum, is equal to 2n. Let's be a little bit more careful about this. We have that a1 plus a2 plus up to an, that is the nth partial sum, is equal to Sn, and that turns out to be equal to, I don't know, 2n over 3n plus 5. If you do some math, you figure out that the first n terms of this particular sequence add up to that. What does the series converge to, and does it converge? Well, this will converge if the limit, as n goes to infinity, of the partial sums exists. And now we can just use our standard limit techniques. This limit is easy to compute. The limit as n goes to infinity of 2n over 3n plus 5 turns out to be equal to 2/3. And so because that limit exists, we can say that the sum from n equals 1 to infinity of an is equal to 2/3. So the big idea here is that by showing that the sequence of partial sums has a limit, we can conclude that the infinite series is equal to that number in the sense of limits existing. All right, so let's talk about the most important, probably the single most important series that there is, which is called the geometric series. Now, you've seen geometric series probably in various contexts. They usually get introduced as lists of numbers way back, maybe even in algebra. Algebra 1, Algebra 2, you may have seen this. But the basic idea of geometric series is that they have this form. A plus AR plus AR squared plus AR to the third, and so on. And the normal form for this, if we're thinking about it as an infinite geometric series, is going to look like the sum from n equals 1 to infinity of a times r to the n minus 1. Okay. So if you think about, have we actually produced the correct sequence here? Well, we can start plugging in numbers and see if we get the right terms. So if I put in n equals 1 into this formula, I get a. If I put n equals 2 into the formula, I get ar to the 2 minus 1, which is ar, and so on. So this is the correct form to produce this series. Now, one of the big deals here is that as long as I'm working with finite sums, I can do algebra on these things. And so we can actually discover a formula for what this adds up to. So I'm going to point out that at some point you probably learned that if this sequence exists, if this sequence converges, that if this series converges, that it converges to A over 1 minus R. So I have not proved this yet, but this is an assertion about the structure of these things, is that this infinite series converges to this number, subject to certain restrictions on the behavior of R. So if it converges, it converges to this. So the way that you actually prove this is you work with the partial sums, and we're not actually going to do that construction in this video. I might show you guys in class. You can walk through it in the book. It basically boils down to knowing how to, there's a special factoring formula that you need to know in order to prove that this theorem holds. But the theorem that's working in the background here is for which values of R does this exist. So R you can think of as being the ratio of the geometric series. And if you think about the behavior of R to the n, if R is bigger than 1, then R to the n goes to infinity. If R is bigger than 1, R to the n runs away to infinity. And if we have infinities piling on, bigger and bigger numbers piling on to an infinite sum, there's no way that can converge. It's just not going to, right? The numbers have to get smaller and smaller as we go out if we're going to have any hope that there's a limit in the sequence of partial sums. So this can't possibly, the geometric series can't possibly converge for values of R that are larger than 1. And likewise for values of R that are less than -1. So you'll get alternation as you multiply by a negative number. The signs will flip back and forth, but it's still getting bigger and bigger and bigger as it runs away. So same deal. If R, R to the n, if R is less than -1, then R to the n runs away to both positive and negative infinity, just with alternate signs. And so the upshot here is this sum can only converge when R is strictly less than 1. So if R is less than 1, or it's less, between -1 and 1 strictly, then when I start taking powers of fractions that are smaller than 1, they go to 0. So the theorem about geometric series is that this thing converges to A over 1 minus R when the absolute value of R is less than 1. So between -1 and 1, otherwise it diverges. So typically when you're faced with the convergence of a geometric series, what you're looking for is the A and the R that dictate the construction of the series. Because once you know A and R, you can just write down if R is less than 1 or bigger than, between -1 and 1, you can just write down what the series converges to. So as an example, we can think about the series that looks like, say, 5 minus 10/3 plus 20/9 minus 40/27, and so on. If I suspect that a series is geometric, the first thing I should do is look for what the ratio is between the terms. So when I look at the series, I think, well, what would I have to multiply 5 by to get 10/3 out? So how do I do this? I mean, the first thing you should always check for is if a series is geometric. When you're considering any series, the easiest series to look at are the geometric series. So you look at that and you say, 5 minus 10/3. So if I'm going to get from 5 to 10/3, I would have to multiply by -2/3 to do that. So this is acquired from the previous term by multiplying by -2/3. Now, if it's geometric, that same multiplication will work on the next step as well. So you look here, is -2/3 times -10/3 equal to 20/9? And it is. This is also multiplication by -2/3. And likewise, this is multiplication by -2/3. So that means we've identified what the ratio is. The ratio that controls this particular geometric series is R is equal to -2/3, assuming that the pattern continues, which of course we're always allowed to do. Then I just need to figure out what a is. But a is just whatever the first term happens to be. So a is 5 because it's the thing in the first position. That's a. And so what that means is I have all the information I need. I don't even need to devolve to sigma notation here if I don't want to. I can just write down what this equals. Because I've identified this as a geometric series with these parameters, I can just say, well, this equals a over 1 minus r, which is 5 over 1 minus 2/3, which is 5 over 5/3, which is 3. So that is a convergent geometric series, and its value that it converges to is 3. Okay, typical of geometric series type constructions. Now, one of the cuter things you can do with geometric series is you can come up with what the fractions are for rational numbers. So let's actually see. Maybe we'll pick a number like 0.12121212 forever. There's a rational number. It's rational because it's a repeating decimal. So it's a repeating decimal. What I'm going to do is I'm going to write this as a series, and I'm going to see if that series happens to be geometric. So this is the same as 12 100ths. That's this part. Plus 12 10,000ths. Plus 12, 1, 2, 3, 4, 5, 6 millionths, and so on. Now, what you should notice about this is this guy right here, to get from this term to the next one, because that pattern repeats, I'm shifting the same number of digits each time. I suspect this is geometric. The pattern seems pretty similar. What do I do to get from the first term to the second one? Well, I multiplied by 100th times 1 over 100. And the same move happened here. And continuing on down the chain, each time I get to the next thing in the sequence by multiplying by 100th. Well, that means r is 1 over 100. And a is just whatever the first term happens to be, which is 12 over 100. And so we could write down that this infinite series (1, 2, 3, 4, 5, 6) is equal to a, so 12 100ths, over 1 minus r, which is minus 1 100th. If you do some algebra on this, what you're going to find is you get 12 100ths over 99 100ths, and so we get 12 over 99. So 12 over 99 is the fraction that produces this particular rational number. So this is a standard sort of exercise that comes along with geometric series. Okay. It's also possible that you might get a series that you need to examine in something like a formula form. So another example you might see would be something like the sum. Here's another example. The sum from, I'm doing an example out of the book here, 1 to infinity of 2 to the 2n, 3 to the 1 minus n. Does it converge or diverge? So at this point we have one tool, which is geometric series. And so what I'm going to try to do is rearrange that formula so that it looks like a geometric series. And the way I'm going to do that was just with algebra. So I need to get something to the n. The pattern that I'm after here is I want a number outside and then some ratio on the inside of the nth power. So that's the game I'm going to play, is I'm going to try to get the 2 and the 3 rearranged so that whatever they are, they're in parentheses and they have a raised to the n outside. And then I'll analyze the series after that. So the first thing to note is that I could rewrite this as 2 to the second to the n. That gets me the first nth power that I want. But then there's this 3 to the 1 minus n. So I'm going to break that up into a 3 to the first times 3 to the minus n, just using the rules of exponents. And so there's this extra 3 running around. And of course, 3 to the minus n is 1 over 3 to the n. So I can rewrite this as the sum from n equals 1 to infinity of 4 to the n times 3 times 1/3 to the n. I've almost got it in geometric form. Now I'm going to smash everything together. All the powers of n come together. And that should give me the sum from n equals 1 to infinity of 3 times 4/3 to the n. Now, this isn't quite right because in the version of this theorem that we used, we have n minus 1 as the power that we want. So remember that I guess the form here was supposed to have n minus 1. We don't have n minus 1, but we can get n minus 1 in there by just pulling one of the 4/3 out of it. So we'll rewrite this as the sum from n equals 1 to infinity of 3 times 4/3 times 4/3 to the n minus 1. I could just pull one of them out to drop the power by 1. So now I've got it in the correct form. It looks like this. And so this is the sum from n equals 1 to infinity of 4 times 4/3 to the n minus 1. And because 4/3 is bigger than 1, this series is a divergent series. So the conclusion is, since r is equal to 4/3, which is bigger than 1, this is divergent. Okay. Typical kind of exercise. All right, so that covers the first part of the series chapter, and the definition of a series, the idea that it is a sequence of partial sums. So what did this video cover? So this is the first part of 11.2. So this is 11.2 part 1. We talked about the definition of an infinite series. We talked about geometric series. I guess we talked about partial sums. We talked about geometric series and their convergence and divergence. And then we looked at a numerical or a list example, a formula example, and a rational number. Okay, in the next part, we're going to talk about computing the sequence of partial sums directly, and a theorem that lets you say when you absolutely know for a fact a series must diverge, which is called the test for divergence. So the next video is going to talk about a different set of examples, both related to the basic idea of infinite series and the basic definitions. But I'm trying to keep these videos around 20-25 minutes in length so that they're digestible. So that's it, and I will post this as soon as I can, and I'll post the second half later today. All right, see you.